Hello, everyone. My name is Mojtaba from KU Leuven, Belgium. This presentation is not a technical one. It's actually an overview of the things that we've done over the past 4 years in KU Leuven in the field of computational biomedical engineering with FreeFEM. So the unit, that's actually our research group in the University of Liège and the University of Leuven. We are focused on mostly tissue engineering and biomechanics, and we have developed a wide range of different models for different processes in tissue engineering. And I want to focus on the ones that we use FreeFEM for. And FreeFEM was really beneficial for us for 3 reasons. The first one was a freedom that it gives us for controlling various finite element spaces. And the second one is actually open exchange formats and interoperability of FreeFEM, to couple it with other models, and also integration with other tools that are quite common in scientific computing, like with PET-C and mesh generation, things like MMG intention and this kind of stuff. So I have, I go through some of the projects, selected a couple of them that are more relevant. The first one is actually my PhD work. I presented it in the previous editions of FreeFEM Days. That is computational modeling of biodegradation process, of corrosion process of biomaterials. So that's actually the material are put inside a body and they dissolve as soon as they fulfill their role. So for example, for fixation application and stuff. But the problem is actually we need to tune the degradation parameters before using them. It can be done experiments or using simulation. So we have a set of reaction diffusion advection equations, as well as Navier-Stokes and stuff, to describe the chemistry that is happening during the corrosion. And it is also coupled with level set formalism for tracking the moving of the biodegradation front. So as I said, I don't want to go to the details of this model, but for this one, I have already presented it in FreeFEM Days. So these are a couple of, just for demonstration, the type of output that we have. So you can see that we have release of material on the left, a degradation happening, and on the right, that's the level set interface evolving over time for a simple orthopedic screw. And this is actually for a porous scaffold that is quite common in tissue engineering. On the left, you can see side corrosion products forming on a surface of this scaffold. And on the left, and on the right, we can see the degradation happening, the shrinkage, the movement of the surface, and also the release of material. So all these things are implemented purely in FreeFEM. This is, for a narrow cuboid degradation that we use mostly for validation purposes, and this is done, visualized using GPU in Purview. And the result of this model is encapsulated, is wrapped in a multifunctional parallel 3D simulation code. We call it BioDeg, that it features a cross-platform user interface, which includes pre-processing and post-processing tools as well. And this can be seen as a FreeFEM, a tool with FreeFEM PET-C backend and Qt C++ frontend. This is something that I presented in the last edition of FreeFEM Days, and this tool is available as an open source tool to download as an example of how you can put an interface on top of FreeFEM codes. And this code is also used, this model is used to couple with other tools. This one is actually a topology optimization code developed in the University of Kyoto, and we come also in FreeFEM, and we coupled these 2 models to have like the mechanical instability at the same time as corrosion. So this is an example of interoperability of FreeFEM in this field. Another project is related to tissue regeneration and growth. So that's also a common type of studies in tissue engineering when you have like cell growth on porous scaffolds. And then, so you put cells, you see cells, and then they start to grow and proliferate, let's say, that's the technical term. And then we want to see that the effect of geometrical characteristics of these scaffolds and how they affect the rate of tissue growth, like the curvature and the shape. And then the thing that we did was actually a computational model of tissue regeneration which was done using an implementation of some moving interface problems with some techniques like level set and phase fill. So in this case, what you see here is actually the FreeFEM output. Like this one, these rows, these are the moving interface as the output of the FreeFEM model implemented in level set. And there is all similar results we have for phase filled implementation. And it can be like used for bioreactors, coupling with fluid flow. And then we have the rate of the tissue growth growing inside these bioreactors. And then we use these models to investigate various types of scaffolds to see which one are better for the goal that we have for having higher rate of tissue growth. And yeah, those models were quite useful for us, and we have like some industrial partners as well working on these projects. And the code was also parallelized, which is a bit non-trivial due to having some level set and phase field redistancing and reinitialization, needing some recollection of the partition mesh and this kind of stuff. But this worked quite well with HPDDM interface in FreeFEM. The next project is related to the modeling of bone fracture healing. So the fracture healing process of bones has different phases, as you can see in a figure: inflammation, repair, and remodeling. This work was focused on the repair phase. As you can see, there are various components here: chemical factors, cells, and tissues. And the interaction of these components can be described using a set of PDEs that are Taxis diffusion reaction PDEs, as well as coupling the whole model with the cellular automaton CA model, also implemented in FreeFEM. So this is a typical output of the model. This is still ongoing and under development, but you can see that it discretized, like discrete model cellular automata, moving cells, so growing cells in the vascular network, oxygen supply on the left, and on the right we have the bone formation as a result of that. So as I said, this is described by more or less 10, 11 equations, as well as a discrete representation of a CA model, all implemented in FreeFEM, and which is also this coupled FE CA model is also parallelized, which was a bit challenging, especially for the CA model. But as you can see here, we have a partition mesh, but the discrete model works quite well. The vessels can grow, jump from one partition to other one. And the bone formation on the right is also the continuous model going on. The next project is related to the modeling of pancreatic islets cells viability, which is actually that the objective was treating type 1 diabetes. So we have the donors and we get the cells from them, and when we want to transplant it, and they need some preparation, they are vulnerable because they need some oxygen. And the way that people investigate it is through like some devices. They put the wells, the group of cells inside these devices, and then for the oxygen, these devices provide oxygen to the cells, and that's something that people do in experiments. But we also wanted to investigate the cell viability in a computational model implemented in FreeFEM. So that's actually a reaction diffusion model. You can see the results for single islets group of cells inside a micro device, and also a couple of them, like in this case 4. And then we had like different parameters being employed in the model to see the most efficient, also from the from the costs perspective, to have the most optimized versions. And then we had like full version, like the full device, multiple wells, the whole device. We have cells, they consume oxygen, and then the supply. And then we wanted to see if the design of the devices are quite okay for the cells to survive or not. So these were a couple of examples for projects, but besides computational modeling, we also use FreeFEM heavily for geometry construction and mesh processing. FreeFEM is quite good to be used as a tool for that. So what I mean is, like, for example, we want to have like an implicit mesh on top of a complex geometry. In this case, the geometry is just something random, it's just a bone. So we mesh it with FreeFEM, and then we apply an implicit function, and then we ask, for example, MMG or Techen plugins to separate, to split a mesh for us and remesh it. So in this case, you can see that we have like a kind of gyroid shape applied to a complex shape, and then remesh it again. And this is something we use a lot in our group. This is another example for a cup, applying a function and then remeshing it using MMG, which can be later used for another simulation. I will show you an example in the end of this presentation. This is another one for jawbone reconstruction. As you can see, the figure on the left is actually generated with FreeFEM. This one, FreeFEM and MMG extension. And also for, after doing this refinement and mesh generation, the things that we need a lot is embedding the mesh inside another one, which is mostly used for biodegradation simulation. And these are also used, we use FreeFEM internal mesh generator and also MMG extension to build these kind of mesh. And then in the next couple of slides, I want to show you an example, a case study of this, which is I presented as an HPC case study because we used a couple of thousand of CPU cores to simulate it and get a strong scaling result. But you can see that how we use FreeFEM in different steps of the modeling workflow. So in this case, we have a cup. I showed you before this. I showed you this one before in a couple of slides back, filled with TPMS lattice structures. This is the output of a topology optimization code, and then we want to see how this degrades actually in a solution or in the body. So we embed it inside a container and we generate a mesh on it, and we refine the mesh because the biodegradation code requires a refined mesh on the interface. These are all done using the pipelines that I showed you. And then the mesh contains, in this case, 45 million elements. This is an animation showing why such a mesh contains this number of elements. So the mesh is quite fine on the interface, and of course, far from the implant surface actually. So this is a mesh for the level set and biodegradation model actually. And then we have the mesh partitioning to 2,000 to 8,000 CPU cores. Implemented using HPDDM. And then this is a simulation results visualized using ParaView, but in a server client manner because we had like heavy results, result files. And this is visualized using 128 CPU cores using remote visualization. So this is actually the output of the FreeFEM model. And this is the results from another perspective, showing how it degrades, and there are a lot of discussion on this from the pathological and physiological perspective. And then on top of this, we had some strong scaling results. This is actually an interesting thing to discuss later on with Pierre probably, because we had some problems with the strong scaling, the simulations, the models to more than 10,000 CPU cores, which was also a source of controversy that FreeFEM is not very ideal for larger scale simulations. And that's something that we can discuss later, but I was quite satisfied with the tools for parallel computing in FreeFEM. And I want to finalize the presentation with some outreach activities. This is something discussed before in previous FreeFEM days. So we have a project in which we share the experiences we have from this project, from these computational models on YouTube in a simplified language. And most of the time we use FreeFEM for that, and they are based on FreeFEM most of the times. And in this project, there is also one playlist we've recently started, which is actually introduction to FreeFEM in a very simplified language. And this is it's still incomplete, but I'm going to complete it with some parallel computing, HPDDM, and PETC stuff in a very near future. So yeah, thank you so much for your attention. I try to be 15 minutes.